Imagine a vast, empty dance floor, a space so large and open it seems to stretch on forever, inviting endless possibilities. Not a single soul is present. The emptiness is almost palpable, a blank canvas waiting to be filled. Now, picture an endless sea of dancers, each confined to their unique space on the floor. They move in harmony, yet each one is distinct, never overlapping with another. This is the essence of the quantum world, a realm governed by a fascinating principle known as the Pauli Exclusion principle. It's a world where the rules are different, yet incredibly precise. In the quantum world, particles like electrons, the building blocks of atoms, behave like these dancers. They follow intricate patterns and rules, creating the structure of everything around us. They each have a unique spin and energy level, defining their place in the atomic structure. This uniqueness is what gives each atom its own identity. This principle, discovered by the brilliant physicist Wolfgang Pauli, states that no two identical electrons can occupy the same quantum state within an atom. Pauli's insight was a breakthrough in understanding the microscopic world. Think of it as a cosmic game of musical chairs, but with a twist. The rules are strict, and the stakes are high. The chairs represent the different energy levels within an atom. Each level is a specific place where an electron can exist. The electrons are energetic dancers, each try to find a seat. They move with purpose, seeking their rightful place. However, the catch is that no two electrons can share the same chair if they have the same spin. This rule ensures that each electron maintains its unique identity. This seemingly simple rule has profound implications for the universe as we know it. It influences the behavior of matter on a fundamental level. It dictates the arrangement of electrons within atoms, shaping the very fabric of matter and influencing everything from the colors we see to the way stars shine. This principle is a cornerstone of our understanding of the natural world, revealing the hidden order in the chaos of the cosmos. To understand the Pauli exclusion principle, we must first venture into the bizarre and fascinating world of quantum mechanics. This realm, often counterintuitive to our everyday experiences, governs the behavior of matter at the atomic and subatomic levels where the rules are vastly different from the macroscopic world we are familiar with. In the quantum world, particles like electrons don't behave like tiny billiard balls that follow predictable paths. Instead, they exhibit wave-like properties, their position and momentum described by probabilities rather than definite values, making their behavior more like a cloud of possibilities. Imagine trying to pinpoint the location of a wave on the ocean. It's constantly moving and changing, never staying in one place. Electrons within an atom are confined to specific energy levels, much like the different orbits of planets around a star, but with a twist. These energy levels are quantized, meaning they can only exist at discrete values, like rungs on a ladder, and not in between. An electron cannot exist between these levels, just as you can't stand between two rungs on a ladder. It must jump from one level to another. Now imagine each of these energy levels as a shell surrounding the atom's nucleus, each shell representing a different energy state. The Pauli exclusion principle dictates how many electrons can occupy each shell and how they are arranged within it, ensuring no two electrons in an atom have the same set of quantum numbers. This arrangement is crucial for understanding the chemical behavior of elements and the formation of molecules, as it determines how atoms bond and interact with each other. The electrons, with their unique spins, fill up the available energy levels in a specific order, starting from the lowest energy state and moving to higher states as needed. This order is governed by the rules of quantum mechanics, and the Pauli exclusion principle plays a critical role in maintaining this order, ensuring the stability and diversity of the elements in the universe. The Pauli exclusion principle's influence extends far beyond the confines of individual atoms. It is the bedrock upon which the entire edifice of chemistry and the structure of matter are built. Without it, the universe would be a vastly different and far less interesting place. Consider the simplest atom, hydrogen. It consists of a single proton in the nucleus orbited by a single electron. This electron occupies the lowest energy level, the ground state. Now introduce another electron. The Pauli exclusion principle comes into play. Since no two electrons in an atom can occupy the same quantum state, the second electron in helium, the next element on the periodic table, cannot occupy the same energy level and spin state as the first. It is forced to occupy a slightly higher energy level. This seemingly minor detail has profound consequences. As we move across the periodic table, Adding more protons to the nucleus and electrons to the surrounding shells, the Pauli exclusion principle continues to dictate the arrangement of these electrons. This arrangement determines an element's chemical properties, its affinity to bond with other elements, and its overall reactivity. The periodic table, a cornerstone of chemistry, is not merely a random arrangement of elements. It is a meticulously organized chart that reveals the fundamental structure of matter. It is a testament to the underlying order and elegance of the universe, a symphony of elements orchestrated by the Pauli exclusion principle. This principle is a key rule in quantum mechanics that governs the behavior of electrons in atoms. Each element's position on the periodic table is determined by its atomic number, the number of protons in its nucleus. This number is unique to each element and defines its identity. However, it is the Pauli exclusion principle that dictates how those elements behave and interact with one another. This principle states that no two electrons in an atom can have the same set of quantum numbers, which influences the arrangement of electrons in orbitals. Elements in the same vertical column, known as groups, share similar chemical properties. This is because they have the same number of electrons in their outermost energy level, known as valence electrons. This similarity arises from the fact that they have the same number of electrons in their outermost energy level, their valence electrons. These electrons play a crucial role in chemical reactions and bonding. These valence electrons are responsible for an element's reactivity and its tendency to form bonds with other elements. The way these electrons are arranged and interact is fundamental to the chemistry of each element. The Pauli exclusion principle ensures that as we move across a period, a horizontal row on the periodic table, each element has one more electron in its outermost shell than the element before it. This orderly progression is what gives the periodic table its structure. This progressive filling of electron shells gives rise to the periodic trends in chemical behavior observed across the table. Trends such as electronegativity, ionization energy, and atomic radius can all be traced back to this principle. Without the Pauli exclusion principle, the periodic table as we know it would cease to exist. The orderly arrangement of elements and the predictable patterns of behavior would be lost. Elements would not exhibit the predictable patterns of chemical behavior that make chemistry such a powerful tool for understanding and manipulating the world around us. The periodic table is more than just a chart, it is a window into the very fabric of the universe.